Okay, great. So now we can move on to the second part for today, which will be a presentation by Lorrenz, Sparrenberg. We'll talk about model inference on commodity hardware.
So Christian has already said that LLMs have not yet won a Nobel Prize. However, they are still very interesting to research at. And what I want to talk about is quantization. And I guess some of you have stumbled over that term already. And quantization does not apply alone to LLMs. Quantization might be also of interest for you if you are working with other model architectures. And yeah, let's have a look into that. How can I switch to the slides? I've never worked with an app.
Okay, so you can just click on the screen. Now you can do it there.
Simple as that. All right. Modern large language models, they are built of hundreds of billions of parameters. Take, for example, DeepSeek. There we know it has the most recent model has 685 billion parameters. Grand 3 Max has over 1 trillion parameters, and GPT-5, Gemini 2.5, we don't know. These companies are normally not sharing more architectural information and details about their models. Well, one drawback is, of course, these model weights, they need huge amounts of RAM. So you need to somehow load the model on your computer to work with it, to crunch the numbers. And this is just insane to work with models with so many parameters. And yeah, think about you are dealing with sensitive data. You want to use applications where you have personal data, or you have applications in the medical field, for example. Then maybe you do not want to send this information to the hyperscalers which are able to run these models. I'm talking about Azure, Microsoft, Amazon Web Services, Google, and so on. And so maybe this is not the best place for your data to be there. And you want to run these models maybe on your own local machine, on consumer hardware. But how can you do this? So, I mean, we have open weight models. So open weight means the model weights are available for us. We can download them from Hugging Face, for example. It does not necessarily mean these models are open source. Open source would mean we have the source code, how these models were trained, the data is available, which is normally not the case. And so these are open weight models. And even if we take some of the popular ones, like when 3.0, 72 billion parameters, or the meta model Lamarr, we still would need 140 gigabytes of RAM on our devices, which is still a lot. So I don't expect you to have that much RAM at home. And yeah, what can we do? Well, model weights are normally stored in as floating numbers. These can be 16 or 32 bits per weight. And yeah, why not use other formats? We can maybe just use int8, int4, or maybe we are crazy and take int3. And yeah, think about, we have a floating number where we need at half precision these 16 bits, and for int8, we only need half of that. And for int4, we can halve that once again. And dealing with models at this lower precision is called quantization. And yeah, in general, I would say we have two ways how we can quantize our models. We can already at training time use quantization-aware training. So we would simulate the quantization conditions, and this would, in general, give us the best results. But I mean, of course, it's computationally heavy because then we need to train our models from scratch. So we just once again have the problem, we do not have the resources normally. Or what we can do, post-training quantization. So we can just download our models from Hugging Face, and then we are quantizing the model weights. Of course, we will get performance degradation, okay, but this is principally open to everybody, and everybody can do this. Well, this is great. And so just to give you an idea how this could work, so let's have a look on the most naive, most basic example how quantization works. So let's take the model weights, and we could just split our model weights into blocks. Let's say 256 weights per block. And let's say we want to quantize to just 4 bits. Well, we're ambitious. And then we can have a look on the min and the max weight we can find in each of our blocks. And in our example, let's say it's just minus 0.5 and plus 0.5. And the weight we want to quantize is minus 0.45. So the first thing we would need is a scaling factor. And the scaling factor is just defined by the min and max of our model and the bit width. And in our case, it would be 0.0667, around that. And we would need a 0 point, which is then defined by the min weight and the scale factor. In our case, this would be, if we round that, 8. And when we then just put everything into this equation, to get the quantized weight, we would just take our weight, divided by the scaling factor at the 0 point, and we would end up with 1. So we have effectively changed the representation of our minus 0.45 value to just 1. And you can think of, okay, this is much more memory efficient, right? And to see, okay, how much precision we lost, we can reconstruct our original weight, and we already see, okay, minus 0.4669, which is of course not the same as minus 0.45, but we're close to that. Yeah, so this is how it could work in the most simple case, and this is also how in a lot of cases quantization is done. But as you can imagine, people are thinking about, can we do this better? Are there better ways? And this slide is just to show you, yeah, of course, this is a very active research field where people are, yeah, they're just playing around with their ideas. Can we subdivide the blocks? Can we maybe have a look on the activations that are passed between the layers? Maybe this is more important. We should have a look on that. Are there maybe certain outliers that should be handled differently? Can we use a calibration set to maybe find better parameters? Ideas. But in the end, what we have and how this works, we are interested in the activations. So we have our model has layers, and the information is passed from layer to layer. And the model is updating these activations between each of the steps. And this is, when I talk with people about quantization, most of them have the idea, okay, yeah, maybe all of the matrix multiplications are just done in the quantized format. I guess there are some frameworks that are using or doing exactly that. But for some of the most popular ones, like Lamarr CPP, they are actually doing a dequantization step on the fly. So we have the quantized model, which then lies in our fast memory. And now we are just loading some of the block weights we need. We are dequantizing these weights on the fly in our very fast CPU or GPU registers. And we are then just updating the activations. And this can be done with the C++ code very fast in sequentially. And this is actually how at least Lamarr CPP deals with these data and solves this problem. Okay, so this is quantization, but now there's the question, can we somehow measure performance degradation? And this is not a simple task. And think about, we just take some of the benchmarks you usually find, like Hellersweg, Winogrand, MMLU. These are the benchmarks people are normally using to tell you, okay, this is my model's performance. My model now reaches a new SOTA benchmark on this data set. That is great. And yeah, just to give you an idea how one of these examples might look like. Yeah, from this data set, the question is Elder Scrolls Online the same as Skyrim? the answer is it's just false. So here we have a classification problem. This is a binary answer. And what people are doing, yeah, they are posing these questions to the model. They are just extracting the answer, yes or no, and we have a classification task. So we can throw our normal metrics like accuracy, precision, recall, F1 score on that. And here's now something I want to talk about with you. Have a look on this here. What we see here, we have the x-axis, and these are now different quantization methods. Starting from the most basic one, Q8, this means this is quantization with integer 8. So we have a lot of parameters, we have some room to represent our numbers, and we get more and more aggressive in our quantization. So we get to Q6, so we have only 6 bits, we have 5 bits, 4, 3, only 2 bits. And the K means this is a certain quantization method. It's called K-quant. If you are interested in that, I can tell you about that later on in the question and answering session. But think about, we have these quantizations here, and it's getting more and more aggressive. So we have different models we had a look on, like, yeah, Lamarr 3.1, Lamarr 3.2, Mistral, the Teuken model, maybe you've heard of that. This is one of the models Fraunhofer IAIS is developing, very interesting topic. The Gemma model, this is one of, this is Google's model, and Vicuña. And we had a look on the accuracy, or more precisely, the relative accuracy loss. So we had a look on the base model, on the accuracy. We just subtracted the accuracy we found with our quantized model, and we just normalized it by the accuracy of the base model. And what we could see, okay, well, for the most aggressive quantization, of course, we have a large difference to our base model, and this now decreases and is here around 0. But if we have a closer look, here are some strange things happening. Like, for example, the Gemma model, these values are negative, meaning, oh, the quantized model gives us a better accuracy than the base model. Okay, well, there might be some reasons for that. And yeah, here on the right side, it's just the average at each step, just for you that you can better see that. And you can see, okay, this method seems to work here for very aggressive quantizations, but Q5, Q5K, Q6, Q8, okay, these are more or less all 0, and there's not much information in that. So what might be the case here? Well, having a look on accuracy, 2 models might have the same accuracy, but they might not have the same answers. Think about, we are just switching some of the answers from yes to no, and then you might have 2 flips, and now you have a look on the other model, and it once again has 2 switches here from yes to no. So we have 2 flips. But if you add them up, they would give you the exact same accuracy. So maybe accuracy is not the right measure to access or to understand the difference between these models. Is this clear to you? Okay, great. And another measure people are using is perplexity. For perplexity, we have the same problem. Maybe we have a sense like the cat is crossing the, and then there is a gap. And a language model is trained to just predict the next most probable token. So you have a token probability distribution. And this probability distribution might give you at the first place street with 37%, then bridge, then roof. And then you have the quantized model, which also gives you a street with 35%, which is almost the same as the 37%. And now just calculating the perplexity would give you almost the same number. But then having a closer look on the distribution, you might see on the third place, okay, here we have room with 10% and here lawn with 15%. And all of a sudden you see, well, the underlying token distribution is not the same at all, but perplexity cannot represent that. So we might be better off to have a look on the distributions, on the logits distributions. So what I mean with, what happened now? This I think is still working. This one is still working.
It's probably. I come back in a second. I might have just.
Okay, biding our time. Here we are.
I'm afraid
Yeah. Computers are alive, they are living beings, so we cannot say what is happening there, and sometimes strange things happen. So just to clarify that once again. So we have maybe the input tokens, like the cat is crossing these are converted into token IDs, just numbers. They go through the model. And the model then predicts, once again, token IDs or token ID distributions. So we have probabilities for each of these tokens. And now we can compare these probability distributions between the base model and the quantized model. And for this, we have different measures. We can have a look on the Kullback-Leitner divergence. We can use the Jensen-Shannon divergence or Wasserstein distance. There are lots of metrics we can use here. And what happens if we apply them to our problem? Well, once again, same graph. We have here on the x-axis the quantization, less aggressive to very aggressive. And now we are looking on the divergence, the Jensen-Shannon divergence for the different models on our benchmarks. And we want to again see, okay, quantization, very aggressive quantization, we have a very large divergence and it goes down. But now we do not see these strange artifacts that they are, I mean, we still have a certain offset. Maybe we can just calibrate for that, don't know. But we do not have these overshooting at certain quantization levels, which do not make any sense. And if we have a look on here, the mean divergence, we see, okay, we can, so please remind, this is not 0 here, this is 0.1, right? And the 0 is here. But just to show you the upper side, here you can see a good difference between all of these quantization methods, and at least they make sense. Well, I like to have complementary approaches to verify, okay, this is actually working. And I took a completely different field, chess. And in chess, we can use the same models. We can just input a chessboard as fan tokens, and the only task the model has is to predict the next probable or the best next move, the UCI move, maybe G2 to E4. And the nice thing here is we have a very defined environment. We know everything here. We can deal with very small models. We do not need these several billion parameter models. We can go down to 5.2, maybe 9.9 million parameters. So this is less than 1,000 still of that. Yeah, we're just training these models, and we can evaluate our games or our chess engines here against Stockfish as a fixed ELO. This ELO here is not great. 1,320 is something every amateur should beat in principle, but we need to start somewhere. Okay, and now we can once again have a look on, okay, how much ELO loss does our model have? And what I think here quite intriguing is if there are errors accumulating in my model, then a chess game is not done after 1 or 2 moves. A chess game has 60 or maybe 100 moves. So if there are small differences between the models, these errors should accumulate. So we would expect that small differences in the weights might hurt ELO a lot. And actually we can see that. So we see for the very small one. For the smallest one, okay, we have huge ELO losses for the very aggressive quantizations, and this goes down to almost zero for the base models. And here we once again see now the same graphs. So okay, maybe the first method with the divergence or the distribution comparisons does make sense. So at least we have another clue that, that here is something. Okay. But then these experiments, they are super expensive. We need to train our models, we need to quantize our models. We need to run the inference on all these data sets. Maybe there is a way that we can already see or what model degradation we can expect by just having a look on the weights of the model. Wouldn't this be much leaner, much more efficient? So maybe there are some patterns we can use. And yeah, luckily Shazeb is here. Shazeb run a lot of these experiments. And yeah, what now Shazeb did, he took these models, for example, Mistral, and he had a look on the different layer types. In the transformer, we have the K layers, we have the V layers, we have the Q layers, the O layers, and all of them can be quantized and they can be compared to the base model. And we can see, okay, how different are these layers compared to the base model? So what we see here are the 32 layers of the Mistral model, the K layers. We are looking here on the Wasserstein distances, and here the different colors are now encoding, yeah, just the different quantizations. Pay attention that the Wasserstein distance here is now on a logarithmic scale. This is because otherwise we would only see the Q to K lines here, and the rest would just be scuffed near the baseline. And you can see, okay, the largest differences are in the very early layers for the K layers. And for the O layers, we see not a downward trend, but more or less an upward trend. And the largest differences are in the late layers. And I think this does make sense because the K layers in the attention mechanism, the very early one, they need to process your input. And maybe there you might expect the largest outlayers or very fine structures that the model needs to understand in order to further process all this information in the upcoming layers. And for the O layers, it's the other way around. The more or the closer you get to the model's answer, the more structured or the more even outlayers you might expect in these layers, which are then just smoothed using quantization. And yeah, and this is what we see here. We see the largest information loss or differences in the early layers for the K layers, and for the O layers, it's in the last layers. So what we need, more experiments. What can we do? Well, maybe we can start with a cumulative quantization. So maybe we quantize the first layer, the first 2 layers, the first 4 layers, the first 8 layers, and we can do it the other way around, and we can have a look, okay, how does this influence these distances? But this is still upcoming work, and Shazeb is still in his master thesis, so unfortunately I expect you to run much more experiments. But what he already did is, how can we close the gap between model performance and these, I can say, yeah, phenotype typical observations where we just look on the model's weights, and what we have here are the activations. The activations, that's the information that is passed between the layers through the model. And Shazeb ripped off one of these models and just had a look on the differences in the activations between all of the layers. And you can see, okay, in the beginning, these arrows, they jump up, then they stay more or less the same. And here is also something happening. And the next experiment we are thinking about is, okay, maybe the first and the last layers are the most sensitive ones, and maybe we should not quantize them at all. So just keep them as they are at full precision. We run this experiment and have a look, okay, how's this now looking? And we hope to better understand, okay, what are actually good quantization schemes, so we get the most of our models, and at the same time, how could we compress the models as much as possible in order to run them on consumer hardware? So the conclusion so far is, well, if we want to run the models on our consumer hardware, so from the technical point of view, we need quantization at the moment, and maybe accuracy, F1 score precision are not the best metrics to address performance loss, but having a look on the logic distributions might give us an advantage or more information. And we now have the hypothesis that not all layers are equally important in a model, and yeah. Can we use this information to find better quantization schemes to improve the overall quantization process? So in case you want to read more about that topic, here's are some references. Thank you very much. And are there any questions?
In an earlier lecture in this very same series, I believe it was held in Dortmund, we had it was also talked about quantization, but not for the purpose of reducing RAM requirements, but for the purpose of reducing energy consumption. I wonder to what extent these the differing objectives change how we have to quantize our networks. I mean, when it came to energy consumption, they even went as far as trying to make the weights binary mostly. They had to make some serious adjustments in that network, I believe, for it to work, but it's whereas here we are even decompressing the weights at runtime and only compressing them for storage.
Exactly.
I wonder how much of an effect does the deep compressing have?
Okay, you are referring to that step. We hadn't had a look on the decompression step yet. However, I think the goals are a bit, or the targets are a bit different, right? So saving energy, and here saving compute power or hardware in order to still get reasonable results. And here I can give you an answer to that, if that's okay for you. So I run some experiments where I could see, okay, very, very aggressive quantization, like 2-bit quantization, is hurting model performance that much that it's actually better to stick with a smaller model. So let's take, for example, Gwen, 72 billion parameters, run that one on the 2-bit quantization. You're better off to use the 32 billion parameter model at 4-bit quantization. This will outperform the 72 billion parameter model. So it's not published yet, these results, but I can already, this is a pattern I could see over and over again. So if you want to get as much model performance as possible to aggressive quantization, at least in post-training, post-training quantization is hurting model performance so much, it's better to stick to the smaller model. Okay, are there any?
Sorry, the questions in German.
Yeah, are there questions on the other side? Okay, people are staying.
Yes, we have one question here, so you can just speak.
I don't know if it's that relevant, but I read yesterday something about misalignments on AI models, for especially competitive games. Like I don't know how the game was called, but maybe there's a problem when larger models give other reasoning and do something else behind it in games to be better in competitive games. And maybe it might affect that smaller models don't fool users on benchmarks, whereas maybe in future even larger models might more fool users with reasoning for competitive games.
You are referring to that there is some that people could find that some of the large models are aware of the testing scenario that they are being tested right now. Do I understand you correctly?
Yeah, so I don't know if there are different impacts it might have, but I think there might be some factors for it.
Yeah, I mean, this is still a huge problem, having these benchmarks, and these benchmarks are published, and you don't know 3 or 4 months later if these benchmark data are already incorporated in the training data of the large language models. So I would say these benchmarks, the results should be taken with you should be careful with them. This is why I added this complementary method using chess, because chess, I would say, you cannot really cheat in chess, right? So, but this is still an open question, I would say, how to really measure model performance in scenarios where you do not have the problem with data leakage in the training data sets. But I don't know how to solve this with quantization. It's not differentiate. There's a question here.
Yeah, actually, I wanted to answer the question he asked. So what he meant, I guess, it's like, suppose that we have a Q2K model and we are running it, and when we are dequantizing or on the fly, then it might take the same space, or maybe it's the same energy power, right? So it might be like what you might thinking, like it's when we are dequantizing on the fly, it might take the same power resources as the original model. But actually, that's not the case. Like, but when we are dequantizing on the fly, it's like for every other layer we are dequantizing, and using that weights and all of those stuff to calculate the next activations. It's like we're not dequantizing the entire model at the same time. So that's why we are not using the entire. Suppose that for the base model, it's taking 14 GB on the GPU, but when we are using the Q2K model, it might take only 3 to 4 GBs at the GPU. So it's not using the entire power resource of that GPU that we are using. So that's why it's a bit more power efficient. But the thing is that, like, when we are using the Q2K model, it's dequantizing on the fly. So it will take a bit more time than the original base model. So that's also the case we have to like worry about. Yeah, we may save power, but at the cost of time.
The I/O load is much faster. You can load the quantized models or the model weights much faster than the original ones at full precision.
Yeah, I would have lots of questions sort of for future research. And therefore I'm asking just one of them. And it's not like what they are doing there and blah blah blah. And I know that it is known if you have a very large network with millions of parameters, and right now I'm not aware, still no, but 10 years ago. And you only train a tenth of those parameters. The others are basically random. That still gives you very good performance.
Yeah.
Because, you know, it turns out you don't have to train every weight, just keep most of them fixed, random values, and the other 10 of them will adjust to that. This can also lead to some compression, right? You give me the model, and then I just sort of fix half of the weights and compress the other half.
And this could also lead to some such patterns, right?
I don't know.
Yeah, maybe. Yeah.
My question is, does anybody think in this direction? Or is it completely not mainstream right now? Because I'm always looking.
I think it's
left
not
and right to the
I
mainstream.
don't think it's it's mainstream, but what I've read about several times is that people are thinking that these models are actually undertrained, which would be the same, right? So yeah, we do not have enough text data.
One of the reasons, sort of like, it's not fully understood, but that is why dropout works.
Yeah, regularization, yeah.
Exactly, and the main observation is, and there's other paradigms where that works. You basically have a random machine and you just train a small part, and that small part, it's basically like in the brain. When you have a stroke, it doesn't matter. A small part will readjust to what's still there, and so you never have to train the whole shebang. It's like this basic. Most of it's random computations, and the trained half will sort of turn the randomness towards where you want to have it.
Actually, we are planning to run some of these experiments, but we might address that. So now we have access to all of these layers, and we can read out the activations. And one of our ideas was to just initialize or perturbate certain layers just with random numbers and see how the model behaves. Can it recover from that by rerouting around that, or does it?
I thought like compress half of the things to 2 bits. And let the other half readjust, and you still should have a huge gain.
Yeah, so maybe we are talking about this sweet spot here. Here, it seems that nothing's happened to the activation layer, so to the activations, and here obviously a lot is happening. So maybe this might be here one of the bottlenecks where we can compress a lot.
I just want to know if anybody is doing that. I mean, there might be a DeepMind paper tomorrow. But it's not a trend to sort of think out of the box and all try to compress everything.
And right now, we really want to understand what's going on there, which layers are the important ones, how they are
Why are there 30 layers? It doesn't make sense to answer the question which of them are important. Why are there 30 is the most important question. And nobody can answer that.
Yeah, exactly.
Like this is
I thought, so I can't find at the moment, but I thought that some people have already tried just dropping them out completely. So taking a free train, because the last layers basically don't do anything anymore, as you say. So just removing them altogether and after training, but you need it during training. That's basically the thing.
I know there is research to make the model aware of the task and to early stop and to just say, okay, I just need 5 layers and not the 32 layers. I can stop here. Here's my answer. But
no, I mean, it's really just poking in the fog. So, like, question, I have 30 layers. Which of those are important? That doesn't make sense. I just, to me, the interesting one, and biological brains have that as well. I can kill a third of your neurons, and after some time, you will be back.
I can recover,
Right? And that is interesting for compression, because that means that you can train a full model and throw away a third of the neurons and let the rest adjust, and nobody's doing that. That is my question.
Okay, I take this with me, and maybe this is something we should have a closer look on into how we can use this knowledge for this compression. Can we use these quantization schemes for model compression? But I still want to perform these noise injection experiments.
This is, I'm not at all judging here. Like this is, I'm super impressed by N3, right? But nobody knows if that's the best architecture. Like, why? Seems to be good if they are large. That is the lesson, but
I mean, 1 trillion parameters. This is insane. This is around the amount we have in our brains.
Any last questions from government?
Yeah, there is. Go ahead.
No questions from here.
Thank you very much.
Thanks very much. Thanks to us. And we'll see everybody here again next week.
It's your machine, I wasn't sure.
Thanks a lot to you in Bonn. And see you next week. Bye.